You see rockets from SpaceX landing on drone ships in the middle of the ocean, or even crazier, getting caught by a giant tower. And you probably think vertical landing is the only way to bring a rocket back to Earth for reuse. Well, China might think differently. There's a rocket company in China exploring a really crazy idea, landing a rocket booster sideways instead of vertically. And the interesting part is, this concept isn't just for show. Their analyses suggest it could actually be surprisingly effective. So how exactly would China pull this off? And more importantly, could this strange method actually be better than the way SpaceX lands its rockets? Let's find out. Founded in 2020 and led by CEO Li Rui, Nayuta Space is still a relatively low-profile company compared to bigger Chinese commercial space names like Land Space, Galactic Energy, CAS Space, Space Pioneer, and iSpace. But the company has started getting attention thanks to one very ambitious idea: landing a rocket booster horizontally. Recently, on April 24th, Nayuta Space revealed that it had completed several new funding rounds, from pre-A1 to pre-A3, raising an undisclosed amount of money to continue developing its partially reusable Blackbird R launch vehicle. These new investments come around 14 months after the company's original pre-A funding round in early 2025, along with several smaller financing rounds in between. First, let's talk about this rocket. The Blackbird R rocket is expected to stand around 70 meters tall, with a 3.8-meter diameter core and a 5.2-meter payload fairing. The vehicle will use liquid methane and liquid oxygen across 2 stages. The reusable first stage is planned to fly with 13 engines, producing around 70 tons of thrust each, while the upper stage will use a single vacuum-optimized engine, generating roughly 80 tons of thrust. With this new funding, Nayuta plans to move forward with a static fire campaign for the rocket's second stage, using a currently unnamed methane liquid oxygen engine developed by a third party. The company also wants to continue wind tunnel testing to better understand the rocket's aerodynamic behavior, while also carrying out more tests of its unusual belly flop recovery profile for the first stage. Okay, this is the part a lot of people have been waiting for. Let's talk about that strange landing method of this rocket. Instead of coming down vertically like Falcon 9, Nayuta's concept uses aerodynamic surfaces to glide the booster back through the atmosphere. Then, during the final phase of descent, the stage rotates and lands horizontally using 6 landing thrusters. In some ways, it almost feels like a reverse version of Starship's belly flop maneuver. Nayuta calls this system ADHL, short for Aerodynamic Deceleration Horizontal Landing. According to the company, the booster slows itself from more than 3,000 kilometers per hour down to around 936 kilometers per hour, or roughly 586 miles per hour, during the glide phase before the landing thrusters take over for touchdown. The company says this method avoids the need for large and heavy landing legs like the ones used on the Falcon 9, although some structural support system will still be necessary once the vehicle reaches the ground. At the same time, Nayuta claims ADHL can reduce propellant consumption, lower engine wear, and keep payload loss to only around 1%, which would be extremely impressive for a reusable launch system. The rocket itself is designed for a wide range of missions, including commercial satellite launches, suborbital experiments, and potentially even space tourism in the future. As part of the program's development, Nayuta recently completed a Pathfinder version of the Blackbird R first stage. The test article is equipped with 4 movable aerodynamic control surfaces designed to simulate how the real booster will maneuver during descent and landing. Early tests have already demonstrated pitch control by moving the forward and aft surfaces at different rates, yaw control through independent left and right movement, and roll control using similar inputs. The company has also been testing more refined control modes, ranging from minimal guidance during descent to fully deployed positions for landing operations. Right now, Nayuta Space is targeting the first half of 2027 for the maiden flight of Xuanyao R. That first mission will mainly focus on successfully reaching orbit while also attempting controlled recovery tests during re-entry to gather flight data and further improve the company's aerodynamic deceleration and landing technology. Now, I know what some of you are thinking. China definitely has a very different approach when it comes to reusing rocket boosters. But how does it actually compare to Starship? Both ADHL and Starship are ultimately trying to solve the same problem: how to recover massive rocket stages cheaply enough to support rapid and fully reusable launches. But the philosophy behind the two systems is completely different. Starship mainly relies on propulsive landing. During re-entry, the vehicle uses atmospheric drag to slow down to some extent, but the final and most critical phase of landing is handled by rocket engines. The booster performs a controlled landing burn before either touching down back at the launch site or being caught by the tower arms. The ship itself is also designed around engine-powered landings for future missions on Earth, the Moon, and eventually Mars. ADHL, on the other hand, is trying to reduce its reliance on engine braking much more aggressively. Instead of burning large amounts of propellant during descent, the system aims to let the atmosphere do most of the work through high-angle aerodynamic flight and horizontal landing techniques. Put simply, Starship's philosophy is basically use engines to control the landing, while ADHL's approach is more like let the air do as much of the work as possible. Because of that, the two systems end up optimizing very different parts of the rocket design. Starship accepts relatively high landing fuel consumption in exchange for simpler aerodynamics. The vehicle remains mostly a giant stainless steel cylinder with comparatively small aerodynamic surfaces. It doesn't require wings or large aircraft-style structures, which helps keep the overall design simpler and avoids major aerodynamic penalties during ascent. ADHL takes almost the opposite approach. In theory, it could save a significant amount of landing propellant, but it also introduces much more aerodynamic hardware into the system. That likely means larger control surfaces, additional structural reinforcement, more thermal protection coverage, more moving components, and possibly even some form of horizontal landing gear. And that's where a lot of the criticism comes from. Some people believe the extra complexity and added mass could end up canceling out much of the fuel-saving advantage that ADHL is trying to achieve in the first place. Another huge difference is how each system handles control during re-entry. Starship's approach is actually somewhat brute force, but very controllable. The vehicle uses aerodynamic drag during the belly flop phase, but the engines remain the final authority during landing. If the trajectory is slightly off, the engines can still correct aggressively during the final burn. SpaceX also has the advantage of very powerful methane engines with deep throttling capability and multiple relights. ADHL depends far more heavily on aerodynamic precision. The rocket must maintain stable control through a much longer atmospheric flight regime while dealing with high angles of attack, heating, turbulence, and changing aerodynamic forces. That means the control surfaces and guidance systems become absolutely critical. Small deviations can potentially grow much larger because the system relies less on engine correction. Thermal protection is another major contrast. Starship already faces enormous thermal protection challenges, especially on the ship during orbital re-entry, but the heating is still relatively concentrated around known regions and flight profiles. A DHL may face even broader thermal exposure because its entire concept depends on spending more time using the atmosphere to bleed off speed. That could spread heat loads across wings, hinges, control surfaces, and larger sections of the rocket body. This leads directly into maintenance concerns. SpaceX's strategy is heavily focused on rapid reuse. Even though Starship still has major refurbishment problems to solve, the overall philosophy is to simplify operations as much as possible and minimize post-flight maintenance. Tower catching also removes the need for large landing legs on the booster. ADHL's critics worry that aerodynamic recovery may create aircraft-like maintenance problems. If thermal protection systems, hinges, control surfaces, or landing structures suffer significant wear every flight, refurbishment costs could become too high. In that case, the fuel savings during landing would not necessarily translate into lower operational costs. There is also a big difference in industrial philosophy. SpaceX pushes engine capability extremely hard. Starship depends on high-performance engines, precise relighting, deep throttling, lightweight structures, and advanced guidance software. The entire architecture is built around the idea that engine-powered landing is worth the complexity because it gives extremely precise control and scales well to very large rockets. ADHL appears to be trying to reduce dependence on those extreme engine requirements by leaning more on aerodynamic deceleration and control. Supporters believe this may fit China's industrial strengths better, especially in areas like hypersonic research, aerodynamic control, and structural manufacturing. The irony is that both systems are basically trading one set of engineering problems for another. Starship accepts high fuel use during landing, but avoids large wings and complex aerodynamic recovery structures. A DHL may reduce landing fuel use, but introduces harder aerodynamic control, broader thermal protection challenges, and potentially higher structural complexity. Right now, Starship has one enormous advantage over ADHL: real-world flight experience. SpaceX has already performed multiple booster recoveries and demonstrated that large-scale propulsive landing works in practice. Even though Starship itself is still evolving rapidly, the underlying landing philosophy has already been proven repeatedly with the Falcon 9 program. ADHL, meanwhile, is still mostly in the validation stage. Its advantages currently exist more in simulations, theory, and early testing than in demonstrated operational performance. That does not mean ADHL cannot work. It simply means it still has to prove that its aerodynamic recovery system can survive real flight conditions, land accurately, maintain low refurbishment costs, and remain economically competitive against more traditional propulsive landing systems like Starship. When Elon Musk commented on the Blackbird R concept, he noted that building a fully reusable orbital rocket, regardless of the design approach, is one of the hardest engineering challenges ever attempted. Much, much harder than going to the moon, Musk said, adding that this is exactly why the problem still hasn't truly been solved yet. ADHL could turn out to be an underrated alternative approach to reusable rockets, or it could end up becoming a very expensive technological gamble. Right now, it's simply too early to know which direction it will go. Who knows, maybe once the rocket finally takes off, it could end up becoming another very unique approach to reusable rockets. And interestingly, the Nayuta team hasn't stopped there either. Just take a look at this image. They've even proposed using their ADHL technology for landings on other worlds, including the moon. That idea, however, doesn't really make much sense for two major reasons. First, the moon has no atmosphere, which means aerodynamic surfaces would be completely useless there. A DHL depends heavily on the atmosphere to slow the vehicle down, so without air, the entire concept basically stops working. And second, you can't exactly send a first-stage booster to the moon in the first place. At that point, it's no longer really a booster anymore. It becomes a spacecraft. In fact, it would end up being much closer to something like Starship HLS than an actual launch vehicle first stage. It's honestly crazy to see that more than 97% of viewers still haven't subscribed to the channel. So if you're enjoying the videos, hit that subscribe button right now. It really motivates us to keep bringing you the best stories about spaceflight. Thank you so much.